Okay, hello everyone. Today is lecture number 9, and we're going to be talking about distributed NoSQL databases. And this is kind of an introduction to that topic, and we're going to have another lecture to finish it up. But last time we had our second lecture on databases, talking about scaling relational SQL databases. And there are basically two big strategies we discussed there. The first was read replication. This was where we took the database and made many copies of the data on it, allowing read traffic to be sent to any one of the replicas. Okay, there still was one master node that was responsible for writing, for receiving writes, and the read replicas got the data from the master. The read replicas could be slightly behind. So it could be some inconsistency where you read after writing a value and don't necessarily see the value that you wrote. However, it's eventually consistent, and because most systems are dominated by reads and more so than writes, this works for a lot of systems. For example, Wikipedia uses this kind of a design, or can use this kind of design. Although with Wikipedia, we also saw there was sort of a different kind of read replication happening on the caching layer up front, okay, with the same basic idea. But this is happening at the database level. Yeah, so that's the kind of horizontal scaling for relational databases. But that only worked for reads. If we want to horizontally scale writes, we need a different approach. We need to actually partition the data. So we can't have all the data stored everywhere on every node, although that would be convenient because it would be a simple design. It means it's limited. It's not scalable because it means that every node has to have capacity to store all the data in your database, which might not be possible. But also because every node is storing all the data, that means that every time there's an update in the system, every time there's a write or a delete, that transaction has to go to every single one of these replicas of the data, right? So that means that every node is handling all of the writes in the system, and that's not scalable, right? You have a single bottleneck, and that bottleneck is not just one node, but actually all the nodes are bottlenecks at the same time. So instead, what you want to do is divide up the data, and give each database node, a fraction of the data. We call that sharding for when we do it for relational databases, and that works well if you can come up with a rule to divide the data that allows most queries to be satisfied with that fraction of the data on one node. But if it's not possible to do that, then you end up querying all the nodes anyway. And we'll kind of see that in this lecture, how that plays out and how to solve that. Yeah, so sharding involves, instead of basically taking all the rows in each table and having some rule to decide which replica, which node that row should be stored in. And that the logic to do that can be programmed in your application, both to decide, and that actually involves a lot of complexity to figure out what series of combination of queries to generate to handle a given data retrieval or a given data update. Okay, but it's doable for many applications. So yeah, to review that, we're with sharding, we're going to be building on that today to generalize it. But the way we described it last time, we were splitting data rows among many machines. This allowed many machines to accept writes, right? So that gave us some horizontal scaling on writes. But the data partitioning was done manually. The programmer had to decide some kind of rule for dividing the data, for partitioning the data, and then write some code that split up the requests and joined the responses that came back. So this all was done based on the assumption that we're still using a relational database, so we're using normalized data. In other words, we have our data split into tables, and we have to do joins to get results from multiple tables. We saw last time a little bit that because the data is split among tables, and all the data required to service any one request in general can be distributed across all the nodes in the system, and that is not scalable because if you're involving every node in every query, that that means that every node becomes a bottleneck in the system. As you scale up the system with more nodes to handle more traffic, you're not really providing any benefit because those additional nodes are not reducing the traffic on the previous nodes because all those previous nodes are being involved in all the requests anyway, right? So today we're going to talk about how NoSQL databases solve this problem by denormalizing the data and therefore limiting the number of nodes that are involved in requests. And the goal is going to be to make queries be serviceable by just a single node. All right, so we're starting off though with the relational model where we have normalized data. Just as a review here, this is an example of a relational database schema with some data in it. And what we have here are a lot of references, so these foreign keys that point to other tables, and specifically they point to rows that have matching values in other tables. Like here, region ID 91 points to the row in the regions table that has the ID of 91 in this ID key column. So in this example here, we have the philanthropy industry is referred to by Bill Gates's profile, but it's also referred to by many different users, right? They're all in that same industry. So this entry here, this relationship or foreign key is linking, this entry in the industries tables is linking many different users, thousands of users. They're all in that same industry. For example, if you wanted to list out do a query that listed all the people in the philanthropy industry, you would have to use this ID 131 to match in the user table to find all those rows, right? And all of these references are capable of requiring us to pull data from another table. And specifically, when we have one row referring to a row in another table, that means that it's possible to build, and likely that you would build a query with a join that would dereference the reference and pull the data from the, child table to connect it with the parent. So for example, if we're looking at users, it's likely that you're going to look up, for this particular user, it's likely you're going to get this row for Greater Seattle, and you're going to get this row for philanthropy. Now, when we're sharding the data, in other words, when we're dividing this data across many nodes, we want to keep the data for our queries isolated into a single shard as much as possible. That means that when there are references, we want to keep those references in the same node. So if we're building out, if we're fetching the page for Bill Gates, that means we're going to do a database fetch for this row, and we're going to join it with the things that it links to. We want to be able to get that data from the same node so that our database request returns more quickly, but also so that we place less load on the system as a whole. So we're only involving one node in one request instead of involving lots of nodes in one request. Okay. So we want to partition the rows into shards. We want to do that in a way that reduces the references between partitions, and this actually is a balanced graph partitioning problem. So we can take the rows in our system and represent them as nodes. So these blue nodes represent rows in the database table, in databases tables, and the edges represent references. So these are foreign keys that point to another row. So for example, this blue node up top that I'm pointing to could be the Bill Gates user row, and it might refer to Greater Seattle, so that might be the node on the left, and it also refers to the industry philanthropy on the bottom right, and that would be represented by edges here. And that means by building a graph like this, those rows in turn might be referred to by other rows, and so we have other nodes that connect to them. If we just do this for the whole database, we get a data row relationship graph of this kind, right? So edges represent references. I mean, technically these should be directed references because foreign keys always point kind of in one direction, references in one direction, but that's really just a detail. We have all these rows. They're connected to each other through references. I mean, they don't have to be connected to each other, but very often they are, and they can be. And if we're partitioning the data for sharding, we need to assign each row to a shard, which means we need to assign each node to a partition. So basically, we need to take the graph and divide it into partitions where, nodes being in the same partition means that those rows are in the same shard of the database. And if you have references within that shard, within a partition, that means that if you're connecting that data, you can do so within that one machine without having to make a network request outside, without having to involve another machine. But if you have references that go between the partitions, that means that if you're doing that join, you have to involve another machine, which is bad. Okay, so the connections in between partitions, bad. Connections within partitions, okay. So we can try to generate a partitioning that minimizes the crossings between partitions. In other words, the number of edges that fall between the partitions as opposed to being within partitions. Okay, so that is a graph partitioning problem. So it's a kind of optimization, a combinatorial optimization problem, where we have to choose like a bunch of disjoint subsets of the nodes that kind of contain all the nodes in total. And we want to do that in such a way that the total edges between partitions, actually, sorry, this word here should be partitions, not nodes. Make a note of that. Should be minimized. The node edges between partitions should be minimized because these represent the potential to have to fetch data from a neighboring partition. And then also we want the partitions to be roughly balanced. So the size, the cardinality of these sets should be roughly the same. So if there are 5 nodes in the left partition, 5 rows in the left partition, there should also be roughly 5 nodes or rows in the right partition. Okay. The reason for that is that we want the storage requirements to be balanced, and we also want the query load to be balanced. Right? Like if half of our data is in one partition, then that means that roughly half the queries are going to go to that partition. Okay, and this idea basically also is there's a paper on Facebook's social graph and how they shard it across their database, which actually goes into a lot of details that cover various things in this class that I have linked to here. So if you have time, there's both a presentation that's about 30 minutes, and there's also a paper. The paper actually is probably better than the presentation because it has more details. But that's a pretty cool look into Facebook's architecture, and we might use that later on in class if I have time as a case study. Okay, anyway, so that's considering the data partitioning or database sharding problem as a graph partitioning problem. Okay, but doing this is kind of difficult for a few reasons. So first of all, just solving this is an NP-complete problem because it's a small change can have a drastic change in the output, particularly if it has to be balanced. If the solution doesn't have to be balanced, then it's a polynomial time problem. It's just a min-cut problem. But if you have to balance the two, it's difficult to solve it optimally. On the other hand, we don't really have to solve it optimally. We just have to solve it pretty well. So that's not a big objection to doing this problem. So we can approximately solve it pretty well. So let's not consider that to be an objection to partitioning. On the other hand, this graph-based model is not really a perfect reflection of how the partitioning will affect our performance because this graph model is a little bit too simplistic. So for example, some of the edges are more important or more commonly referenced than others. So for example, if you have a user that's very popular or a region that's very popular, then the edges connected to those nodes could have much more weight, or should have more weight in your problem because you're going to be more frequently querying on that row or node. And then finally, another reason why this is too simplistic is because the simple count of the edges doesn't fully capture the cost. If you have a row here, like if we still consider this to be the Bill Gates row, you might do a query that fetches, for example, all of the users that are in the same industry as Bill Gates, right? So Bill Gates is not directly connected to everyone in the same industry as him, but he has a reference to the industry, which is here, and then that in turn connects to all the other people in that industry. So you can do joins. If you do a query that has more than one join, then you can pull in data transitively across multiple hops away from the edges. So just giving this edge a cost of 1 if your queries involve multiple joins, could mean that you're undercounting kind of like the cost of having this connection, this reference across the partition. But this is a starting point anyway, and I'm showing this not to show that this is the way this problem is solved and the way that partitioning is done. I'm actually showing this as a justification for why partitioning data is actually really difficult and why we don't try to partition data like this. I mean, you can try, and again, the Facebook paper kind of shows that a little bit. But you're only going to get so far with this kind of approach. So even if you can optimally compute these partitions, you're still going to have references between the two partitions. So you can't totally eliminate the communication to multiple partitions when you're doing these sharded queries, unless your graph is really simple and it has, for example, no connections. Like if you had users in the United States of Facebook and none of them were friends with users in Europe, then that graph would not have any connections between the US cluster and the Europe cluster. So if you ran this kind of a partitioning algorithm on it, you could actually split the graph into two pieces that had no interconnection between them, and that would be great because you could operate in parallel and get that horizontal scaling with perfect horizontal scaling in that sense between those two partitions. But that's not realistic, right? So the problem is in most realistic data sets, there's no clean partitioning. There are always like things that connect to other. The graph is connected to a high degree, I guess, to a high extent. There's no way to easily split it with only having a few edge crossings. So I want to ask you to stop and think about the graph here and how the graph structure affects the solution quality. In other words, the number of edges that come between it. So are there certain kinds of graphs that have good solutions for partitioning, and there are certain kinds that have bad solutions, and what is the difference between those different kinds of graphs and different kinds of data sets? So stop and think about that. All right. I kind of already gave the answer to this, but having a lot of kind of random interconnection is bad. Like if nodes are equally likely to be connected to anyone else, so in other words, if rows are equally likely to reference any other row, irrespective of what partition they're in, then that would make it difficult to assign a node to a partition, right? Like if this node here is connected to basically everyone at random, then no matter what partition I put this node in, it's going to be connected to other partitions. If there are more edges, that's bad in general, right? So if nodes have high degree on average, or then it's harder to split them up with having a low edge crossing cost. On the other hand, there are certain kinds of graphs that are easy to partition. Those are those with very structured data that has independent relationships, like the example I gave before of like a cluster of US users of Facebook, a cluster of European users of Facebook. If those users like speak totally different languages, for example, and they don't share a common language, then they probably are not friends. They're probably not talking to each other on Facebook. So you might be able to partition those users very easily on the basis of language. Now that breaks down in real life because many people speak multiple languages, so they're going to have a lot of users that are part of these two different communities that at the surface, from superficial analysis, might seem like they were separate. Some other things about structure: if you have a node that only has one edge, sort of like dead ends or spokes, those are really easy to assign to a partition because you just assign it to whatever partition the node they're connected to is in, right? Because that's the only thing they're going to possibly communicate with. All right. So I'm showing this as a motivation mainly for jumping to NoSQL databases. So the picture at top was a way for us to think about doing sharding to do data partitioning of relational databases. So we kind of said in the last slide that we hoped our data was such that it would allow an easy partitioning. Like hoping is not going to get the job done. If we want to really like force partitioning to work well, then one way to do it is just to eliminate references. So just make edges between nodes impossible, which means make references between rows, foreign keys, make those outlaw them, make them impossible. If you eliminate references, if you eliminate foreign keys, then you're not going to have queries that join together two rows, and that means that you can satisfy your query entirely from, if your query involves one row, you can satisfy it entirely from one partition. I mean, on the other hand, if you're doing a query that scans a whole table, then maybe that would involve the whole database, but that's inevitable. Yeah, those kinds of queries are always going to be inefficient. Yes, our goal really is just to make the queries involving one data element efficient. And eliminating references is one way to do that. Okay. So that seems like kind of so we go from this picture on top to the picture on bottom. Like we just remove all the edges, and once we do that, it's really easy to partition, right? So that's basically what NoSQL is. NoSQL is a way to it removes references between rows, and it does that for the sake of making partitioning data easy, and for the sake of reducing the possibility that when you do a query, you're going to have to involve different partitions, more than one partition. Okay. The problem, though, is that foreign keys and references are pretty fundamental to relational databases. The whole concept of defining tables only really makes sense if you have references. We'll see that in a second. Okay. So we're going to make a big shift. So this graph looks a little different. But then when we look at some examples, we'll see there's a drastic difference in the way we represent data when we no longer have references. What we end up having is what's called denormalized data instead of normalized data. So basically the idea is, instead of having, if this node up here is Bill Gates, instead of having it refer to other rows, for example, for the industry and the region that he's in, instead of having it refer elsewhere, you're going to actually take that data and pull it into the node, so it's self-contained. So these nodes are actually a little bit bigger because they've pulled in all the referencing data. Although I guess in the picture I could have showed them a little bit bigger. I'll do that next time. Yeah. So at the left we see the normalized data for this Bill Gates LinkedIn example, and on the right we have a NoSQL denormalized representation of the same thing. Instead of having all these different rows that connect to each other, we're not allowed to have references. If we can't have references, then the only solution is to kind of take all that data and slap it all together and store it. In this case, I'm using JSON. It doesn't have to be JSON, but JSON is just a convenient way of representing this sort of structured data. Right? So, industry is listed out here directly as philanthropy instead of having industry 131, which has to be dereferenced to the industries table. And similarly for positions, I have two rows in this positions table for bills, two jobs. Instead of listing them here and then relying on a reference backwards to the user ID, I have actually listed them out explicitly with all the details that used to be in the positions table. I just put that into my big user profile object. Okay, then did the same thing with education. Okay, so there are no references in this data, right? It's all kind of it's all dereferenced. It's all explicitly written. If I want to get Bill's user profile, I just fetch this one row. It's a row that has a lot of data slapped into it, but it's one row. Okay, so it can live in one partition, and that query to build his profile is very simple in the sense that it only refers to one partition or shard, right? All right, so why exactly did we do it in this precise way? You may have noticed a few weird things about this. We only have one column for all this data. I mean, one apart from the key. So the key here is this user ID 251 that he had before. But then I have all this data associated with him, and I put it in one column instead of, theoretically I could have built a really wide row that had lots of columns for all these different values. And some NoSQL databases kind of sort of give you something that sort of looks like that, but they aren't really true columns. Yeah, so we can't. So the reason why we have just one column and gave up on the idea of true columns in the relational database SQL sense is that we can't really define ahead of time how many columns we're going to need. We can't define a schema for this table apart from this general key value thing, because the things we're storing in here include a lot of many-to-one relationships that list out many things. So for example, we have many positions, we have many different education things, education schools. So we couldn't have, a position. If I guess the only way we could solve is by having a positions column that listed out many things in it. That would be okay. But it's kind of equivalent to, because the columns are not referring to other tables, and because the columns can't be indexed, which we'll see, and we'll see why later. There's really no point in having multiple columns, as long as if we can just put the data in here. I mean, it might be helpful to sort of index within this value, and NoSQL databases do that. And it's kind of like a 2D key value store where you have an index for the keys, and then you have an index within every value to get between. Like if this is very long, you might want to have an index for that. But that's very different than columns in a relational database. Yeah. You also may have noticed that there's just one table. And the reason for that is related to the last question, because we don't have a real schema. We just have a key and a value. Like key and value can be applied to anything. So we can use that for any kind of data. So we might as well just have one table. Again, some NoSQL databases do allow you technically to define multiple tables, but in the low-level implementation, there's really no difference between those tables. For example, you might just have a different, like a prefix to the key that allows the same ID to be present in multiple like pseudo tables. Okay, so these NoSQL databases are key value stores. There's one key that's indexed, and then there's a value. The precise format of this value is different depending on the NoSQL database. And so to motivate this and to show how this is scalable, we need to look at hashing. Okay, so hashing is the basis of these NoSQL databases, and that's how data partitioning is done. So you probably know that a hash is an algorithm that takes a value, returns some kind of pseudo-random value from it. It's a constant but unpredictable mapping. So if you give the same input to a hash function, it always gives you the same output, but it's kind of hard to predict what that output would be if you just have, if you look at the input, unless you have an implementation of the algorithm. If I just change uppercase S to lowercase s, although the input looks very similar, the output is totally different, right? That's why I say it's pseudo-random in what the outputs look like. But it's predictable, right? So if you have this key and you know what the hash algorithm is being used, in this case MD5, then you can generate the hash the same as anyone else, and you'd get the same hash value. It can be applied to short keys and also to really long keys. Like this is a novel that has 800,000 characters, and you can compute an MD5 hash of that. So these are useful for like error correction. For example, if you have a file, you know what the hash was originally. If the file is manipulated and one of the bits is changed, if you recompute the hash, you'd see that the hash output is different. That would give you a clue that would tell you that the data had actually changed. Okay, so that's hashing. I'm sure you've seen that before. I'm sure you've also seen hash tables before. Hash tables are a way to implement a dictionary or map, abstract data type. So you store a key and value pair, and this dictionary or map data type just takes a key and maps to a value. You've certainly seen that. And the way that hash tables work are that you have some kind of buckets to store the data. You compute a hash of the key, and that gives you a number that can be somehow, probably with a modulo operator, translated into a bucket number, and then you store the value there. Because the size of your hash table you don't want the size of your hash table to be as big as the range of hash values. So when you sort of compute the modulus of the hash value, you're likely to come up sometimes with a bucket that already stores some data from a different key. So for example, John Smith and Sandra D both map through the hash function to 873. That's called a collision, and there's simple strategies for dealing with that, like maybe hashing again, or linear probing means that you just go to the next slot or bucket until you eventually find an empty one, or you can have a linked list here that you add to. Those are hash tables. Okay, so hash tables are useful for indexing because, in constant time, you can figure out where something should be stored, right? So this is similar to the way that we talked previously about tree-based structures for creating indexes on database tables. You can, with a tree in log n steps, you can traverse that to figure out the location of a row. Similarly, with a hash table, you can actually in constant time figure out the location of a row in a database table. So in some sense, it might seem like a hash-based index is a great way to implement an index for a database table, and sometimes they are used, but one downside is that you can't do range queries as effectively because like with this tree structure, you can very easily kind of like find the neighbors to move across the values in the as you scan through the database, whereas with hashes, you'd have to kind of look through the whole hash table to figure out where the adjacent value might be. So that's all review of hash tables, but what's important about hash tables for scalability is that they give you this really nice way of sort of like almost load balancing, it's like a system you can use to figure out where to go to perform your service. In this case, the service we're performing is storing data. So if we want to store data somewhere and that data is distributed across many different nodes, we can compute a hash of the key of that data to figure out which of the different nodes the value should be stored in. So one way of looking at this is we take a hash table and we split it up into different chunks or partitions according to just ranges of hash values, and we assign those ranges to different nodes, right? So a client, if it wants to use this, now we have a distributed hash table. So this is a huge hash table. The data is distributed across 3 different nodes because one node is not big enough to store it all, and one node is not fast enough to handle all the requests. So instead, if the client knows what all the nodes are, what hash values are stored in each node, let's assume those are just like hard-coded. In reality, you need a distributed consensus algorithm to deal with that changing over time and getting the correct answer. That's a detail. Anyway, the client, if it knows what the nodes are and what hash values they store, it can just take the key if it's querying by key, that's an important thing also, and with a hash table you always are. Then you have a key, you want to fetch the data, so you hash the key and then use that hash to figure out what node stores it, and then you ask that node for the data. And then internally each node would just have a regular hash table probably to store the data. So you can efficiently find the data either for reading or writing, right? So pretty simple, but a cool idea and very useful for scalability, one of the fundamental building blocks for scalable systems. And it was kind of originally developed, since in the Google Big Table, I think, paper. So this is like late, like around 2000 is when these kinds of systems were developed. The idea was pretty simple, but that was, I think, the first time when companies were starting to get to the scale where they needed to scale databases in a way that was much more scalable than the relational databases that previously had been built allowed. All right, so a distributed hash table is an implementation of a NoSQL database. Stores key value pairs, and it doesn't support like SQL queries. It only lets you get input. So it has that abstract data type of the hash table of the map that hash table implements. But the key thing here is that every operation only affects the one node storing that key, or you might have multiple. We'll talk later on about replication, but assuming with the simple design, you have one node that stores the key. So that operation to get or store a value only goes to that one node. And importantly, you don't have to ask anyone like which node you need to contact. Like there's not a central directory that could become a bottleneck. The only centralized thing is distributing to all the clients a list of what the nodes are and what ranges they are handling. Right. Now, this doesn't support full SQL or any kind of references, because those joins, like we kind of said at the beginning of the lecture, those joins to dereference would involve pulling data from many nodes, and that eliminates the scalability feature we have that only one node is involved in every query. So in this case, if we have a distributed hash table design, what limits the scalability of the system? So I'm going to actually have you think about that for a minute. It's a pretty difficult question. So go ahead. All right, hopefully you took a minute to think about that. So reads and writes are kind of infinitely scalable, actually, which is kind of a strong statement. But you could go to like thousands, or I don't know. You can certainly go to thousands of nodes. If let's say you try to go to millions or billions of nodes, like at some point it gets to be too large, and why? Okay, so remember what the clients are doing is taking a key, computing a hash, and then checking a list that they have of all the nodes in the system and what ranges of the hash range are where each node is assigned in the hash range. So I compute a hash, I get the value 8, and I need to figure out which of the nodes is assigned to hash value 8. So each client needs to store all of the nodes and the ranges associated with them. It has to be able to find them efficiently. So really the only thing that limits the scalability is the ability for the clients to have a list of all the nodes in the system. Now, just storing the list and indexing through it is really easy. So you could easily have millions of nodes stored in the clients. So that doesn't really answer the question. But where you really have a problem is when you do have millions of nodes. That means that on any given day you have many of them failing and being replaced, and new ones coming on and stuff like that, right? So there's a lot of churn in the system. So that list of, let's say, 1 million different database nodes has to be updated constantly and redistributed to all the clients. So that kind of sharing the latest information and the correct information about the full list of nodes to all the clients is what becomes a bottleneck finally and prevents it from being infinitely scalable. If you only have 100 nodes, then it's easy to have that information be distributed to all the clients and for it to be up to date, because it's a small enough number that you're not going to have changes that often. Okay. So this is a distributed shared nothing architecture. There's no data shared among the nodes, at least in the first design. We can build a cluster, connect them up with some kind of networking, and tell the clients some configuration information, like what are all the IP addresses of all the nodes and what hash ranges are they handling. And then you can start reading and writing, and the system works very well. So there are a lot of NoSQL distributed databases based on this basic design. And examples are Mongo, Cassandra, and DynamoDB, and others. There also are distributed file systems built on the same kind of principle. And that includes the Google file systems, the different iterations of that. And that's, I think, Bigtable was probably the first academic paper that talked about using a distributed hash table, but it was actually for a file system. And Hadoop HDFS, Amazon S3. The way that the type of data that's stored and the way it's stored might be a little different, but you still are, a distributed file system is still a kind of a distributed database in the sense that you have data you want to split among nodes, you want to be able to get it. Because we've simplified the things you can do, it's not we're not talking about SQL databases. We're talking about databases where you just put and get using a key. If you think of that key as a file name, including the path, all the slashes that go up to the final file name, and that's and actually Amazon S3 uses the term key instead of file name or path. If you think about it that way, then a distributed file system is really has the exact same interface or abstract data type as a NoSQL database. It's a distributed hash, and it can be implemented with a distributed hash table. Cool. All right, so distributed hash tables, NoSQL databases are great for scalability, but they're downsides. And like I said, it's not a very complicated idea, but it wasn't introduced until about 20 years ago because of all these downsides that it brings. Okay, so the relational databases are really a lot more powerful in terms of the indexing and efficiency if you're okay with fitting your data in one machine. All right, so let's look at these downsides. So first of all, we have just one indexed column, which is the key, so the like primary key or the key. There's only one key. The reason why we only have one key, we can't, like, for example, we can't have a key on the last name. Like with a SQL database, you could have you have indexes on multiple columns, and that would allow you to efficiently, for example, get all of the LinkedIn users that have the last name of Gates. To do that efficiently, you'd have to have a index on this last name of Gates. Instead, the only way we have to efficiently get the data in this case is by the ID of the user. Okay, we can't get this data here. This value I'm showing cannot be retrieved in any other way with a different key, because the key with this hash-based system of partitioning, we're using the key to decide where the data lives, like what node it's on. And if we had multiple ways of doing that, that would mean that the data had to be stored in multiple places, and it wouldn't be consistent. And it could be, when it was updated in one place, it wouldn't be reflected in the other. Okay, so we have one indexed column because the indexed column is the way because partitioning depends on that index. Another downside is that when we've denormalized the data, we introduce duplication in the data. So for example, this greater Seattle area text up here in the relational design was just a little number, 91. Now it's this long text. So it's taking up more space. This is not a great example because it's actually still pretty small, but you get the idea. The greater Seattle area could be an object that has a lot of data associated with it, like what's the population, what's the climate, what's the latitude and longitude, what are the geographic boundaries. Like there could be a ton of information about greater Seattle area, and if we denormalized this profile, we would potentially store all that data here under Bill Gates, and that big chunk of data would be repeated for all those other users in greater Seattle area. Okay. So it's wasting space. It also can't be edited in one place. So if, for example, greater Seattle area population changes from 1 million to 1.1 million, and I'm storing that information in a denormalized manner in all of these user profiles, I have to go through all the user profiles that are in Seattle and change them. So they're kind of two related benefits of normalization that we lose now by denormalizing. We don't have references, but we could add references back. Like, for example, if we wanted to avoid that problem with greater Seattle area being big and having to be changed everywhere when it changes, we could create a new row for it, and we'll see at the very end why that doesn't work very well. But basically, that means that we have to follow those references, we have to do a second query because there are no joins, because there are no true references. And that second query very likely is going to have to go to another node because it's being placed based on a hash of the ID, which is going to place it randomly, right? So if we start to do references to try to go back to something that's sort of like SQL with normalized data, then we're going to do lots of queries for each to build these profiles, and that's going to be slow. It's going to be not scalable because it's going to involve like lots of nodes in every request. And there's also no constraint checking on those references. So if we had, for example, region 91 listed up here, and there was a region 91 row, if that region 91 row was deleted, we would not know that. We could, in a relational database, you can configure your foreign keys to either set it to null when it's deleted, or you can prevent the deletion if it's being referred to somewhere. In this case, that data is not necessarily going to be in the same machine. So these NoSQL databases don't build in any way to have foreign key constraints checked and to prevent inconsistencies. Okay. All right, so looking at this, or thinking about NoSQL, right? I listed a bunch of downsides of denormalization. However, I mean, a key value store does give you the flexibility to store references in a normalized way. So you could actually still follow the design of having many tables like this. And I was kind of talking about this before. So you could have like the user table store just information about the user, and then it could have some references. You see these numbers like position 458 and position 457. The details of those positions could be stored as additional rows in this this NoSQL database, right? So I'm using a prefix on the keys to indicate essentially which of the pseudo tables it belongs to. So we have position 458, and that's here. 457 is here, and you kind of join these together to build out all the data. Again, region 91 is listed here, and then finally the education schools are listed here as well, right? So you can do this. Now, as a review, I want you to stop and think about why isn't this done? Actually, I just told you it's possible. So one of the questions was, is this possible? I'll tell you right now it is possible, but why is it a bad idea? Or when is it a bad idea? It's not always a bad idea, but what makes it a bad idea in some cases? What's the downside of this approach? All right, so stop and think. All right, so hopefully you stopped and thought. The downsides are basically that when you're doing a query that in SQL terminology did a join, which is to say took this user row and connected it to all the references it has, then that's going to involve doing additional queries after you do this first query. So first you have to fetch this data. You get it back, you read it, you figure out what the references are, then you do those queries. You could do those in parallel. But you have a two-step process. When you get those, you might need to do additional queries if you're doing multiple joins, but let's say you're not. Even then, you've done, instead of one query, you have many queries. So why is that a problem? They're smaller queries, right? You might say. Well, first of all, there's a round trip time for every query, so even if they are small, you're like making it slower. But the biggest problem is that you're involving multiple nodes. Like you don't know, these rows are being placed using hash-based partitioning, so they could be on arbitrary nodes in other throughout the system. So you're by involving lots of nodes in this query, you are making it unscalable. And in this case, there's kind of it looks like there might be a constant number of other nodes because there's a small number of references, but in general, there might be lots of positions, which would cause lots of queries. Now, I mean, you can use this kind of a design. It's not terrible if you can tolerate the fact that you're going to be, make one query, then make a bunch of other queries, and the overhead of doing, let's say, 5 small queries compared to doing one query that returns 5 times as much data from one place is much greater, right? In the normalized design here, all of this data was stored in one contiguous chunk of disk or memory. It's much faster to get that than to, even if it's on one machine, than to go to like a bunch of different locations on disk to fetch that data, because the disk has to rotate, the ARM has to move, and even in memory where there's no physical there's no mechanical movement, there still is a big delay, much bigger delay to access different parts of memory because of the way caching works. When you access one location, you pull in like all the nearby memory locations. Yeah, so another problem with this design, in addition to the slowness of it, you have references that are not enforced by the schema, so they can become broken. Like industry 131 could be deleted at some point, and user bill would have the kind of dangling a reference that was invalid. All right, so that wraps it up for today. So we talked about NoSQL databases as a kind of a different way of doing data partitioning. Data partitioning in general is necessary to divide data in a way that makes the write load scalable, so we can horizontally scale write operations to a database. We saw this last lecture with sharding of relational databases. And regardless of whether you're talking about sharding with relational databases or NoSQL databases, you want to minimize references between partitions. In the relational case where you're actually you have a lot of references between rows, you can look at those references as a graph partitioning problem and try to minimize the number of references between partitions when figuring out how to divide things. And you could try to, there are some research databases that try to have a relational database that automatically like partitions the data based on the references and the traffic and whatnot. But in general, it's a difficult problem, and it's not done in real systems as far as I know. SQL sharding we saw last time was a special case of data partitioning done in application code. Okay, but with NoSQL databases, generally we do data partitioning using hash of a key, and we call that a distributed hash table. We divide the hash space evenly among storage nodes, and the client just has to know what nodes are in the system and what hash ranges there are assigned to them, and then the client can then directly go to the responsible node when it's querying for a key. In doing that, and when switching from a relational design with tables and references to a distributed hash table kind of model, we lose the richness of SQL and we have to denormalize our data. That means we have to either duplicate data and also allow inconsistency. That's like the full denormalization approach. Or we can do something in between where we still have multiple rows that refer to each other. But the problems there is that the data can become inconsistent, and also more importantly, there's a performance cost. You have to do multiple queries to get the different parts and stitch them together in application code. And then when you're doing that, you're going to be connecting to lots of different nodes, and that kind of reduces some of the scalability benefit. All right, so that's it for today.